Hey, hello everyone. Today I'm going to talk about building multi-tenant, multi-cloud streaming engines at trillion event scale. This is a story about platform evolution mostly and lessons learned during that evolution. Uh, so the mission of this platform is simple: allow teams to write streaming applications without bothering about infrastructure. Something which can manage different workloads with various shapes, few messages per hour to millions of messages per second. Simple ingestion, transformations, complex stateful processing, minimal enough so teams can choose a right engine for the use case. We start with the use cases, what kind of as the company has, ad tech, customer experience, supply chain, transactions, fraud detection, etc. Then assess whether each team is building their own silos, solving the use cases. Standardize it so that it becomes a force multiplier. For streaming use cases, there are multiple great open source alternatives available. Each requires areas of expertise on how to integrate, secure, scale, and save money for the company. For very large scale companies, like biggest retailer on the planet scale, where data sources, sinks are geolocated in different countries, clouds, hundreds of teams, most solutions fall short or need extensive plumbing to fit into the company ecosystem, which is why we end up building something that can solve shared problems for the teams. A cohesive ecosystem by layering the open source engines with existing tech layers within the company. A vision for the platform is based on a set of design principles that we have. Keep it operable, enable self-service, keep it secure, reliable, and trusted from a data quality perspective. It should align with your own company's building principles. Every team benefits from them automatically. Now, let's look at the ecosystem. Like I said before, there are so many great open source alternatives available for us. For this talk, we'll focus on three of them: Kafka Connect, Spark, Flink. This is based on what your company really needs, different users, personas, sources, sinks, etc. In general, Engine should have broad adoption and community support. It should help us solve very broad set of use cases and be able to make it work on similar operating model. Now, what architectural choices enables us to create such complex real-time platforms, right? For building a serverless platform, users should specify the intent. Platform takes care of the operability, observability, keeps it reliable, and provides data quality integration. We chose Kubernetes, which is excellent choice for building such platforms. It allows us to extend the cloud native principles. Most of the engines have strong first class support for it, allows us to easily abstract cloud vendor specific quirks, and it also has excellent semantics for extensibility using controllers and operators, which makes platforms easier and predictable. It's easier said than done, and having layers help companies. Most of the company providers have different Kubernetes operating. Pretty good open source fleet managers are available too. Using them pays off pretty well, especially if you have a very large fleet spanning multi-terabytes or petabyte scale compute. Below that, you have the streaming engine product layer and how they complement each other. This is where Kafka Connect, Flink, and Spark are exposed as self-service products. Now, they're all excellent in their own ways. They have their core strength, and business use cases determine which are used by which customers. Platform control plane on Kubernetes helps with the shared abstraction needed for us. Customers don't really care about it, won't even know if the K8's layer is completely replaced by an alternative compute engine in the future. Now, let's start building the plumbing that is needed. First step is to provision the compute clusters, install the same tooling across clusters. And once tooling is installed, we open it to the customers. They identify their teams, resources, reserve the resources that they need, and let us know what they want to run. We take it from there and ensure it runs in their desired cloud or region, and ensure that it is always running without hiccups. Let's start with going deeper into the products itself. So Kafka Connect as a service, the platform support standard connector patterns like JDBC sourcing, Kafka to Kafka replicating, cloud storage syncs, Debizium CDC, custom connectors, etc. It's a distributed engine suitable for simple transformations and filtering. Customer specifies which provider and region they would like to deploy their app in. They reserve the necessary memory CPU needed for all their apps. They will then have to specify you know, whether they want a metric-based auto scaling, min-max settings, and other configs needed through GitOps or API. After that, the platform takes it from there, provisions it, enables golden signals for the customers, and right sizing recommendations that are needed for future. Spark and Flink are pretty similar too. The customer defines what they want to run. They declare their intent and say, hey, run this Spark job for me. These are my configs. These are my secrets. Call me on this number if anything happens, right? So platform then builds the jar, finalizes the intent, then decides where to run. For example, Google, Prod, Central, Azure, non-prod, South Central, like that. So it abstracts all these things from the user. For them, changing a cloud or a provider is is pretty much like changing a configuration, and it takes care of taking that intent, splitting it into multiple intents. For example, Spark job, certificates, secrets, etc., and submits all of them to selected cluster. So we use a concept of controllers to enable that across the control plane level. Now, this is where the intent becomes the actuals, right? Each of the intent has a corresponding operator, which then takes the definition and creates corresponding resource. Spark, Flink operators, infra operators for taking care of observability, cluster, apps, secret management operators, log shipping to central repo, all are provided within each Kubernetes cluster. It's a cellular architecture. We try to keep a balance between the scale versus sharing the resources so that there's no single point of failure. Now, K8's extensibility using operators and controllers are what makes this stable and operational for us. For many functions, there are excellent open source operators that are available. The platform composes these operators into an ecosystem. It also extends Kubernetes using custom controllers, operators where needed. Uh, it's kind of like a 75-25% need right now. Now let's look at some of the controllers that are needed in detail. The placement engine, which is kind of like the controller that is required to deploy the different shapes of apps that we get, right? It could depend on the size, latency requirements, different hard constraints. Like some people want only in a particular provider, region, etc., depending on their sourcings, etc. So we use a custom scoring function that decides which cluster is best suited during the deployment time based on various multivariate bin packing algorithms. This can easily make the decision between spending uh, you know $10 million, $20 million versus like $100 million. So the easy part is out of the way. Now, streaming apps run all the time. Disruption happens in multiple fault domains. So the infra, app logic, data, everything needs to be automatically identified, mitigated, and recovered. For BCDR, we need custom controllers that can react to cluster issues, failures, and it should have quota-aware, data preservable decisions that it can take in moving all these jobs to their respective intent specification. We also use custom controllers for upgrading all our fleet. The upgrade cycles, they can create disruption as they're not aware of the behavior of these underlying workloads. So we employ a different node pool blue-green pattern where the control spins up a new K8's node pool on the newer version and then moves these workloads gracefully in a coordinated way and scale down the older version. It helps us with the partial rollback too. Security patches, vulnerabilities, they take a chunk of time for us. So, so we need to use like golden images, cluster-wide policies that can be auto updated, which is how we do it. Now, um, so the observability forms a key to the entire platform. Now, if a customer wants to know what is going on with their job, is it running fine, etc., and we want to alert the customer, uh, we employ the different pillars at different layers, uh, Prometheus operators, log collection, eBPF-based profilers that continuously track the network data. So, and everything is fed to the AI to summarize it and be able to troubleshoot quickly to identify the patterns and tell the customer what is happening. Anything that runs on the platform would be tagged with the corresponding labels. There are Kivana policies that automatically do it for us. They make sure that we are able to charge back the customer exactly for what they use. So, by making these hard parts predictable, the platform wins by helping customers be able to, you know, take their applications faster. We enable workload isolation at the platform level, all the upgrades, etc. We try to take care of it in the back end, at the infra layer. Runtime upgrades, we provide the customer with runtimes so that they can update it whenever they have the need for it. We eliminate the operational blind spots, each team having to solve it, and also reduce the cost by providing elastic compute uh, through these products. This helps us save a lot of developer time, improves the overall efficiency within the Walmart ecosystem, within our company's ecosystem, and also saves a lot of cost for the company. The key takeaways here. Um, so, by providing these serverless platforms, we ensure that customer uh, does not need the minimal knowledge that is required. They're more worried about their business use cases and the product that they have to use. We try to keep it as a single platform for multiple streaming engines so that pretty much everything is covered for. Deep observability is built in from day one so that customer is aware of what is happening within their applications and how to mitigate them. Costs are kept to a minimal. All the right sizing recommendations we take care of at each product level. We kind of determine what it is using, what are the query patterns, what are the shuffle things that it is utilizing, and we bubble that information up to the customer so that they can use it to minimize their resources. And we also put the appropriate guardrails for all kinds of production incidents at multiple fault domains so that we try to take away that burden from the customer.
Nice.
Yeah.
Well played, Revanth. I appreciate this, man. Thank you so much. I am going to, let's see, let's get this out of here and I will get to say thank you. If anyone has any questions for you, I'm going to direct them to the chat because I've managed to not do my one job, which is keep us on time. So that means we're going to swap you out for our next speaker. For folks with questions, you're going to hang around and answer them in the chat if you got them. But for
Mhm.
now, thank you, and I bid you farewell.
Thank you.